Hello, and welcome to a little bit extra on the one-dimensional projectile motion activity, number 5. Now, if you were in class, you would see this as a demo, but if you're not, I'll try to explain it to you here so that you can still understand what we're doing. So in number 5 in the activity, we said imagine what would happen if we threw the ball straight up and let it come straight down as we did in experiment on number 3, but this time it was underneath the motion detector instead of above the motion detector. So it would look like this. Notice the motion detector here is above it, so hanging above it now. So what would that do to the graphs? Well, again, if you're in class, I'll show you the graphs, but here I'll try to show you theoretically what it would look like. Here's a position time, velocity time, and acceleration time graph, and here's what they would look like. Watch that again. Notice that the dotted line represents the highest point for the ball. Right? Now, why do they kind of look opposite of number 3? It's because of where the motion detector is. Remember that the motion detector thinks of itself as 0. It thinks that moving away from it is in the positive direction, and moving towards it is in the negative direction. So notice this is completely opposite of a conventional coordinate system. Normally, down is negative and up is positive. But in this system with the motion detector, up would be negative and down would be positive. So the ball, starting way down here, is actually way up here on the graph. It's a large positive position. Then it's getting closer to the motion detector and slowing down, and then it's getting further from the motion detector and speeding up. In other words, it has a large negative velocity towards the motion detector, slows down to 0, that's the highest point, or the point closest to the motion detector, and then speeds up away from the motion detector, which is down, which in this case is positive. And since the slope here is positive, the acceleration is positive. Now you might say, wait a minute, I thought the acceleration was always negative. Well, that's when the motion detector is on the ground. Yes, gravity is still the net force acting on the ball the entire time, and gravity still acts down towards the ground. But down towards the ground is away from the motion detector, and therefore the motion detector thinks of it as a positive acceleration. What would the motion map look like for this? We'll watch this in real time. In this motion map, the blue dots represent positions at equal intervals of time. The red arrows are velocity arrows, and the green arrows are, of course, acceleration arrows. Watch it once more. Now let's take a look at this motion, and why does the graph look, or why does the motion map, look the way it does? Well, on the way up, notice a couple of things about the dots and the arrows. Notice that the dots get closer to one another on the way up. Notice that the velocity arrows get shorter on the way up. And notice that the acceleration arrows point in a direction opposite to the motion. All 3 of those things are signs that the ball is slowing down. Again, the dots get closer together, the velocity arrows get shorter, and the acceleration is pointing in the opposite direction it's moving. It's pointing down when it's moving up. All 3 of those are indications of slowing down. At the highest point, on the other hand, the velocity is instantaneously 0. The ball is at rest, but it doesn't stay at rest. It's still accelerating. And notice it's accelerating the same as it is on the way up and the way down. These acceleration arrows are constant. Now, how do we know it's accelerating? Well, think of it 2 ways. First of all, from a Newton's second law perspective, at the highest point, gravity is still pulling down on the ball. And so gravity is still providing a net force and therefore accelerating it just like it is on the way up and the way down. Secondly, if it wasn't accelerating, if you thought, oh, 0 velocity means 0 acceleration, what would that mean? Well, that would mean that the ball would go up, get to its highest point, and stick there. Because something that isn't moving and isn't accelerating doesn't move at all. And the ball actually comes back down. So what's it doing at that highest point? Well, look at the velocity arrows. Just before the highest point, it's going up. Just after the highest point, it's going down. So what's it doing at the highest point? It's changing direction. And that too is acceleration. On the way down, on the other hand, the dots are getting further apart. The velocity arrows are getting longer and longer. And notice now the acceleration points in the same direction it's moving. All three of those things are indications that the ball is speeding up. Dots getting further apart, velocity arrows getting longer, and acceleration arrows pointing in the same direction it's moving. There's a whole heck of a lot going on in this case. One other thing I would like you to look at in this motion map, look at the beautiful symmetry. And it's symmetric as long as this point right here is the highest point. So we have to assume that this dot, as I did in my in the earlier slide, is actually the highest point dot. Then it's symmetric. Now why is it symmetric? Well, since the acceleration is the same on the way up as it is at the highest point as it is on the way down, the ball slows down on the way up just as fast as it speeds up on the way down. And since it's doing that, two things have to be true. Corresponding dots are going to be at the same height. Right? Those dots, notice, are right next to one another. This is the vertical position reference line. Right? So these heights are all the same. Again, the heights here are the same, the heights here are the same, and the heights here are the same. Because it's speeding up just as fast as it's slowing down. Now, here's the other one. Look at this velocity arrow. And you might notice my velocity arrows on the way down actually didn't fill the space between the dots, which is kind of weird because they normally do. But think about it now. If it is speeding up just as quickly as it's slowing down, how fast is it going here compared to here? Ah, that's right. It's going just as fast here as it's going here, just in the opposite direction. So velocity arrows at corresponding positions are the same length. See, those two are the same speed. Those two are the same speed. Those two are the same speed, but opposite velocity. You may want to go back and make sure that your motion map has all of these little points of symmetry on there, because that's a complete understanding of the uniformly accelerated one-dimensional projectile motion.